In this video, we will be studying about structures of metals, unit cells, and crystal systems. So let's begin. What is a crystal structure, and especially what is a crystal structure of a metal? So basically, crystal structure, as you can see over here, that it is a manner in which atoms, ions, or molecules are arranged in the space. So basically, in this figure you can see that these particles or these atoms are arranged in a particular manner, and basically this manner or this pattern you can say is repeating layer by layer, and it would also be repeating itself in the in the third dimension as well. So here we can see that what is crystallinity. Crystallinity is basically repeating or a periodic array over a large atomic distance, which we can see over here, a 3D pattern in which each atom is bonded to its nearest atom. You can see that in this figure, a crystalline solid, you can see that the atoms are following a particular pattern, and in the non-crystalline solids, we can say amorphous solids, you can see that there is no pattern being followed, or there is no long range order, which we will be discussing later on. So moving forward, what is unit cell? Basically these are certain terms which we have to study while studying the crystalline solids. So basically a unit cell is, as you can see here, is a very small repeating unit. Basically you can say it as a building block, a basic building block of a crystal structure, and this would define the entire property of the crystal structure with the atoms position within. So it means that if this structure is a cube, all the 3D array, or you can say the crystal lattice, would be cubic. So basically a unit cell in the crystalline structures define the basic property of a crystal lattice. You can see that this whole we'll be calling it as a crystal lattice, in which we can see that there is a unit cell which is being repeated in all the directions, that is that could be forward, backwards, top, bottom, and right, left. So it would be repeating, the unit cell would be repeating itself in all the 6 directions. So there are several crystal systems which we will be discussing one by one, and they have certain lattice parameters. Basically these edge lengths, the length, breadth, and the height, and the angles are the lattice parameters of the crystal system. So first of all, very basic and very easy. You all know that a cubic crystal system which has all the sides equal, that is the length, breadth, and the height would be equal, and all the angles would also be of a 90 degree. And moving on, hexagonal. In the hexagonal system, you can see that there is a hexagon on the top having 6 sides. So you can see that in this the lattice parameters A and B are equal, but the third one, the height, is not equal, and both the angles of alpha and beta are 90 degrees, and the other gamma angle, which is opposite to this side, would be 120 degrees. So moving on to tetragonal, you can see that it is similar to cubic, but one of the side is not equal to the other two, that is the height over here is not equal to the length and the breadth, but the angles alpha, beta, and gamma are equal to 90 degrees. So here are some other crystal systems as well. We have rhombohedral here, which is also called trigonal. In this you can see that all the lattice the edge lengths A, B, and C are equal in length, but the interior, the interaxial angle, that is alpha, beta, and gamma, these angles are not equal to 90 degrees. So that means there is no perpendicular or right angle side. So in orthorhombic, you can see here in orthorhombic that again it is similar to the cubic, or you can see this similar to the tetragonal, but in this all the angles are equal to 90 degrees, but none of the side is equal. You can see over here that the length A, the breadth B, and the height C all are not equal to each other. Then we have monoclinic crystal system, in which again all the sides are not equal to each other. That is, the length, breadth, and the height is not equal to each other, but the angle alpha and gamma are equal to 90 degrees, and the beta angle is not equal to 90 degrees. So in triclinic, what we have is again none of the sides are equal, and nor the angles are equal to 90 degrees. So all the sides have different dimensions, and the angles are all also not equal to each other and not equal to 90 as well. So these were 7 crystal systems. We studied cubic, hexagonal, tetragonal, rhombohedral, orthorhombic, monoclinic, and triclinic. So we have 3 very common crystal structures in metals, that is a PCC structure, that is body centered cubic. Then we have FCC face centered cubic, and we have HCP hexagonal closed packing. So we'll be discussing these FCC and PCC in detail. Here you can see that certain elements having certain crystal structures. First of all, aluminum you can see has FCC, cadmium has HCP structure, chromium has BCC, again cobalt has HCP, copper and gold having FCC structures as well. Iron you can see is BCC. Here alpha iron is written if the iron is in the state of gamma, that is austenitic iron, so it would be FCC. We'll be discussing that as well in the later slides. Then we have lead, which has an FCC structure. Then again molybdenum, which has a PCC structure. Nickel, platinum, and silver has an FCC structure. Tantalum has BCC. Titanium alpha. Again here you can see that alpha titanium has an HCP crystal structure, but at a higher temperature this structure changes. Then we have tungsten with BCC, and zinc with the hexagonal closed packing structure. So now let's start with face-centered cubic, that is FCC, very common. FCC atoms are arranged at the corners and center of each cube face of the cell. So what is happening in FCC is basically we have one atom at each corners. We have 8 corners of a cube. So we are basically discussing the cubic structure, cubic system over here. So we have a cube, and it is face centered. That means we would have one atom at each face as well. So this is the front face. You can see that there is one atom here, and the rear face that has the atom this. The right side face that has one atom. The left side face that has this atom, and the top and the bottom face having atoms as well. Also we have atoms at each corners. So we have 8 corners over here: 1, 2, 3, 4, 5, 6, 7, and 8. So we have 8 corners as well, and we have atoms at the face as well. So the A is basically the edge length, that is this side, And in a cubic system, you know that this A is equal to B and equal to C. That means that all the sides, the length, breadth, and the height are same in the cubic structure. So this is not a simple cubic, but this is a face-centered cubic. So we have calculated this edge length equals to 2r under root 2, which we'll be discussing in the other video as well in detail. So before studying more characteristics of FCC and PCC, let's give a thought to this coordination number and atomic packing factor. So basically, what is coordination number? The number of other particles that each particle in a crystalline solid contacts is known as its coordination number. What does it mean to say that in FCC or in any structure, the number of one atom is in contact with how many other atoms? So basically that is the coordination number, that a single atom is in contact with how many atoms. So this is coordination number, and the atomic packing factor basically tells you that how compact your cube is, and that means that how tightly packed the atoms are in a cubic system or in any crystal structure. So basically, SCC structure has one of the most tightly packed atoms as compared to BCC, and the percentage volume or the volume density of these of the unit cell is also high. So basically, the atomic packing factor APF is equal to the volume of atoms in a unit cell. That means that the volume of the actual atoms in one unit cell and divided by the total unit cell volume. So basically, you are finding over here that how tightly packed your unit cell is, or how tightly packed your atoms are. So if we count the number of atoms first in an FCC structure, so basically this is an FPC crystal structure in which you can see that we have atoms at each corner, at each 8 corners, and one atom at the face. So we have studied in the unit cell that if this is an atom, this would be in contact with 8 other cells. So we'll be dividing this atom, this corner, this atom at the edge in 8 equal parts. So we'll be taking 1/8 of the atom at the corner, and we have 8 corners, so we'll be taking 1/8 atom at each corner, and we'll be multiplying it by 8 because we have 8 corners over here. So will be the total number of actual atoms would be 1 at each corner. And for the face, you can see that this face atom would be shared with the other unit cell as well. For this one, the top, bottom, and the rear ones as well. So we have 6 faces, and in reality, only half of the atom will be counted. So we have 6 faces. So we'll be multiplying this half atom with the 6 faces. So we'll be getting 3 atoms. So the total number of atoms in an FCC unit cell would be 4. That is 1 corner atom and 3 face atoms. Okay, so the coordination number and the atomic packing factor of FCC. So the coordination number of the FCC structure is 12. That means that one atom is in contact with, or is arranged with 12 other atoms, and the atomic packing factor, which is calculated, is 74%. That is 0.74. So that means that it has a volumetric density of 74%, and only 36% has the empty spaces. So now the BCC crystal system, which means body-centered cubic. So in a BCC, atoms are arranged at the corners of each cube uh, of the cube with another atom at the center. So basically, what we have is we have one atom at each corner, and one atom is in the center of uh, the unit cell, as you can see over here. That from its name, it is derived as body-centered cube. So there would be one atom in the center of the body of the unit cell. So this is basically the body-centered cubic system, in which again the length, breadth, and height are the same. So we have calculated this edge length, or you can say at the lattice constant A, which is equals to 4r divided by root 2. So there is a lot of geometry involved over here, which we'll be discussing in the other video. So now let's find out the number of atoms in the BCC crystal structure. But before, you can see over here that the BCC APF, in BCC the APF is 68%. That means the volume occupied by the atom is less. But in FCC it was about 74%, or you can say 0.74. So let's calculate the number of atoms. You can see over here that again we have 8 corners, and like FCC, the corner atoms is shared with 8 other unit cells in the lattice. So we'll be taking 1/8 of each atom, multiplying it with 8 corners like here, and the total number of atoms which we'll be getting would be 1 atom, and in the center we have a whole atom. So we'll be adding up the 2 atoms, and the total number of atoms would be 2 in BCC. So now we have hexagonal closed packing. In this, the cell of an HCP, or hexagonal closed packing lattice, is visualized as the top and bottom plane of 7 atoms. Basically, it has 7 atoms which are forming a regular hexagon. As you can see over here that uh, there is a hexagon, and in each corner there is 1 atom, so 6 atoms in a hexagon, and 1 in the middle, so there are 7 atoms, and in between there are 3 whole atoms involved as well. The total number of atoms in a unit cell is 6 in case of HCP. We're not going into detail. And also the coordination number is 12. That means that one atom is in contact with 12 other atoms. And again, you can see that the atomic packing factor APF is 70%, 74% is the same as in the FCC case. So again, the hexagonal closed packed structures are more dense than the PCC structures. So next we have polymorphism and allotropy. So basically, what is polymorphism? You can see from the word that poly means many, and morphism means the morphology or the structure. Existing in more than one crystal structure is basically called polymorphism, and in elemental solid it is called allotropy or allotropic form. So here is an example which is given of carbon. That is, you can see over here that is graphite, the arrangement of a graphite, the arrangement of a diamond which is tetragonal. You can see over here, and the BC8 which is trigonal, I guess. Then we have fullerene, which has 60 atoms. Then we have carbon nanotubes, these hexagons, and we have graphene. Basically, graphene is the only a single layer of graphite is called graphene, which is basically in one dimension as well. you can call it. So here you have different polymorphs of carbon. You can say that means carbon, the chemical the chemical property or the chemistry of all these is basically carbon, involved carbon, and for the structures of each graphite, diamond, VC8, graphene, nanotube, carbon nanotube, and fullerene, they all are made from carbon, but they all have different structures. So next, the other example is basically the example of iron, which I was discussing in the previous slides. That alpha iron, you can see over here, from room temperature to 912 degrees Celsius, has a PCC structure. So when we are heating it to 912, we will retain the BCC structure of iron, and when it will go beyond, it would transform its phase, which we'll be discussing in the later videos, or the later lectures in the course. That it transforms, iron transforms into the gamma iron, which is called the austenite phase, and this has an FCC crystal structure. So again, when we heat it above 3094 degrees Celsius, so it again changes from FCC to BCC until it melts. So you can see the transformation iron from BCC to FCC and again to BCC. So would be transforming while heating, and again it would also be transforming when we'll be cooling it from the high temperature. Okay. So here we have some allotropic crystalline forms of some metals. You can see over here that cobalt has an FCC structure at room temperature, but at a higher temperature, which is 447, greater than 447, it converts itself into BCC. Cobalt again, it converts from HCP to FCC. Hafnium, a noble atom, which again converts from HCP to BCC structure at a very high temperature, that is 1742. Then we have iron, which we discussed in the previous slide. We have lithium that converts from BCC to HCP around 193, minus 193 negative. Then we have titanium, which is again converts itself to HCP into BCC at above 883 degrees centigrade. Then we have yttrium and zirconium, which again converts itself from HCP to PCC structure at a high temperature. So you can see that the same structure also changes with respect to temperature. Not in all the elements, but usually in transition elements it changes. So now we have amorphous solid. Basically, amorphous are the opposite of crystalline. Here you can see that we have a silicon dioxide crystalline material, which is quartz, and you can see that is in a regularly arranged pattern, but we see over here that amorphous SiO2 silicon dioxide, which is in a glassy form. Actually, you can see that there is no particular arrangement of these silicon and oxygen atoms, and these small chains are not in a longer order, as you can see over here that the order is being followed. But here in the amorphous solid, the amorphous silicon dioxide or silica, the pattern is not being followed. So let's read it out. Any non-crystalline solid in which the atoms and molecules are not organized in a definite lattice pattern like glass, rubbery, or polymers, etc. So whatever we discuss is basically written in this slide. So let's discuss some differences between some very basic differences between crystalline and amorphous solids. So in crystalline solids, we can see that the atoms are arranged in a regular three-dimensional pattern, but there is no particular pattern being followed in the amorphous solids, as we discussed in the previous slide. These crystalline solids having a very regular pattern have a very sharp melting point. That means it would have an exact melting point, but an amorphous solid, on the other hand, would never have a particular melting point, but it would have a range of melting points. Third, the crystalline solids would have an anisotropic property, which means that the properties would be changed in several directions. But in the amorphous solids, all the properties are like strength, like mechanical strength, tensile strength, or whatever properties, they would be isotropic. That means the properties would be same throughout the planes, the length, the top plane, the bottom plane, the right, left, and the front and rear plane. So next we can see that the crystalline solids are symmetrical. Basically, they follow a proper symmetry, but amorphous solids are not symmetrical. They are more rigid, the crystalline solids, but the amorphous solids are usually not very rigid, and they follow a short range order, but the crystalline ones follow a long range order. Here we have an example of crystalline solid, that is potassium nitrate and copper, and in amorphous solids we can see that cellophane and PVC polyvinyl chloride as an example of amorphous solids. So now we have polymer crystallinity. Basically, a polymer has both the characteristics, that is of a crystalline solid and an amorphous solid. Here you can see that this polymer is basically around 99 to 100% crystalline, and then the crystallinity decreases. On the left you can see over there, and the polymer becomes very randomly oriented, and it is called amorphous. So you can see that this is a perfectly crystalline solid. Then the crystallinity decreases. The long range order over here, which has been followed throughout, is now not followed accurately, and then the order is disturbed throughout. These chains, these lines are intermingled towards the left. So in any polymer, you won't be having a perfectly crystalline structure or a 100% amorphous structure, but there would be some of the polymer, the structure would be crystalline, and in some of that would be amorphous. So there would be a mixture of properties of both the properties of crystalline and amorphous. This structure is basically of liquid silicone rubber. So how can we calculate the degree or the percentage of crystallinity? That means how much crystalline or polymer is, or our material is, and how much the material is amorphous. So here we can find the percentage crystallinity, and the rest would be the percentage of amorphous part in the polymer or in the material. So we can calculate it by the densities of crystalline solid and the density of amorphous solid, and the PS, the rho S is the density of the whole specimen, the actual density basically. So we'll be using this formula to determine the percentage crystallinity of our specimen. So these are basically densities again, and you can see that rho C and rho alpha or rho A, which is the densities of amorphous part and the crystalline part. These are measured experimentally. we will be having experimental values. We'll be also doing an example problem with this formula with percentage crystallinity in the later videos. So stay tuned. Here is a small activity for you guys to do it. So what we are having this, that is, you have to determine the following for a crystal PCC crystal structure unit cell in terms of an atomic radius. So what you have to do, you have to derive a relation ship using the radius basically, and you have to find the value of this lattice constant in terms of atomic radius, and the volume, which could be this a cube. And so you have to find these two in terms of the radius. It's very easy. You can also consult the book of William F. Smith and William Callister. And next you have to calculate the following values of the BCC metal shown in the figure. You have to calculate once you derive the formula or once you derive the relation of this lattice constant in terms of radius and the volume in terms of radius, so you can easily calculate the lattice constant and volume of the PCC structure only, which is shown in the figure. So you can see that chromium is BCC, iron is BCC, molybdenum is BCC, tantalum is BCC, and tungsten is BCC. So what you have to do is you have to find the lattice constant and the volume once you get the relationship in the part 1, and in part 2 you have to find the actual values using these formulas of the BCC metals that is shown in the figure on the right. Okay, so I hope you will have fun doing this activity. This is a very small activity, and it would be a lot of practice for you and learning for you. So thank you so much.